In this chapter, we will look at linear models for regression. We will utilize the intuition which we have obtained from the chapter 1, where we had the example of polynomial regression based on several data points, and we will generalize this one specific case into a more generalized approach. Furthermore, we will be looking at sequential approaches. We will try to understand the geometry of the linear models, as well as the bias, variance, decomposition, and other topics. So let's recap. The regression is a method to estimate based on a given set of pairs of an input vectors and an associated target values to be able to estimate for a new value of x what will be the corresponding t, and use the statistical machinery for quantifying the uncertainty associated with the outcome target value. So we will be modeling the predictive distribution of probability of t given x, and that's the goal. And the approach to that is to minimize the expectation of a certain loss where we will pick some suitable loss function. Often the loss function can be, for example, sum of squares which between the estimated function y and the actual target values, or y of x and the estimated target values, and we can perform a square of difference of these values, and that error function could be a suitable loss which we are trying to minimize. The simplest regression is using linear functions of input variables. That means that we will be looking at linear at lines which will be approximating our data points. So lines, meaning straight lines, will be then forming the simplest regression, and the line will be applied to all the dimensions associated with the input vector x. But there is more useful will be to look at the linear combination of a fixed set of nonlinear function of input variables, and these are while these are nonlinear functions, it will be a linear combination of them, so we will still have the linear models. And these models of linear functions will define values for parameters w, and they will be nonlinear with respect to the input variables. So if we look at the simplest form of regression, the linear regression, where we are only approximating our data points with n-dimensional lines, then linear function is a set of it is linear in terms of the parameters as well as in the case of input variables. And here we can see how we are basically performing a linear combination of coordinates of the vector x with the weights vectors, which are the coefficients of our weights vector. Please see that we have here d terms for the x and d plus 1 term for the w. So we are weighting each of these dimensions, let's say in 2 dimensions, we will be just weighting the x and x1 and x2, but then these will define us a certain line. However, we also need a bias term, which will be performing a certain offset of this line from the origin. So without this bias term, our function, we can see that in case of x1 and x2 will be 0, it will be going through the origin. And if our approximating line should go through our data points, it needs a certain bias term which can offset it appropriately. So we would be often representing our linear models where we have the bias term either treated separately, and then we have a product of a weight with x in case of the linear regression, or x coordinate in case of linear regression. In case of a more general setting, we are having here some kind of feature function phi j of x vector. So here we can also reformulate this by putting the bias term into the sum, that we will have the phi j generally defined, but phi 0 will be just a value 1. So we will be having a product here, but for the case of phi 0 it will be 1, and for the phi j equals is higher than 0, we will have values which will be, we will have this feature function will be forming as could be formed by some arbitrary function which is suitable for representing then our points, data points x and their corresponding target values t. Please note that while in the previous case we were somehow defining the sum from 1 to d, for d standing for dimensionality, or t plus 1, including the bias term, here we have a more general iterator, which is going until m minus 1. So we have certain complexity which is decoupled here from the dimensionality. So we can see, for example, that for polynomial functions, the m could be the governing factor of the polynomial degree. So m could be for this phi jx could be just like x vector powered by 0, x powered by 1, x powered by 2, and so on until m minus 1. And we can formulate also our sum of these individual coefficients of the w vector and the feature vector as the dot product between these two vector formulations. So we can see that in this case our linear models are represented by this generalization of a function phi. But what can be this function phi? We said it could be we could have polynomial basis functions where we already had one basis function, polynomial basis function, which was linear. So this was a polynomial of degree 1. Now we can have polynomials of higher degree, like polynomials of degree 2, 3, and so on. And this this function, these basis functions, can be seen here. So we have here polynomial degree of degree 1, then we have of degree 2, then we have the next one of degree 3, then again next one which is convex 4, the one, sorry, yeah, convex, then the one which is odd is 5, etc. So we have polynomial basis functions depicted here. These basis functions are also known to be global. So if we change our W coefficients for one of these polynomial degrees, we will change the entire function by that. So a small change of this function or their weight will actually have a global impact. Now, this is not as this sounds to be the most intuitive basis function, because we want to use, for example, cubic curves for shaping somehow and forming this estimate function y of x, which will be representing the highest likelihood of being the value for a given vector x. This is not the only form of basis functions. We can, for example, also have basis functions which are so-called Gaussian basis functions, and where we can see that the exponential term here has a certain formula with parameters mu and s, where the locations are basically defined by this mu j, and the scale is a parameter. So, and such Gaussian basis functions can be actually local. So they will not have their change or the weight will not have a global influence on the rest of the curve. Then we can have other functions as basis functions. For example, the sigmoidal basis functions could also be forming our phi j set of basis functions, where the formula will basically be sigma, and here we have the argument x minus mu j divided by s, and this is again characterizing as the locations and the slope of this sigmoidal basis function. The sigmoidal basis function has this formula, so this argument here will be basically coming into this instead of this parameter a. Other basis functions include, for example, the hyperbolic tangent basis functions, where we can see the formula could be somehow similar to the sigmoidal basis functions, where instead we have 2 sigma and the argument is 2a. So whatever is here, it will be multiplied by 2 and then minus 1. Because otherwise this function will be not defined on the proper range of values, if it would not be minus 1. Then we have the Fourier basis functions, where we are essentially representing a complex function, or I mean complex in terms of its structure, and by expansion of sinusoidal functions with various frequencies, which are then added up. And the final example for linear basis function models are the wavelet basis functions, which are similar to Fourier basis functions, however, where there are also low and high frequencies, and we essentially with their basis functions model certain levels of detail, from the more rough representation to a more adding gradually more and more details to it. So let's have a look at the calculation of the maximum likelihood and the least squares, again, also in this generalized setting. So we can generally say that a t target value should be the outcome of our function, which is estimating our t plus a certain epsilon because of the added noise which is acting upon the target value t. The epsilon can be characterized as a Gaussian random variable with defined a certain precision and a mean around this estimated value y for a given input vector x and the learned parameters w. For squared loss, we have already learned from our chapter 1 that the optimal prediction for y will be satisfying the condition that it is the conditional mean or conditional expectation of t given an x. So if we have for a given x, we have a certain set of t values in our sample set, and they are forming a set of values, and their mean value or their expectation value should be the one which is achieved by the function y. So this doesn't really tell us what is the function y. It just tells us that on this position x, it should be not equal to the value t, because there are generally several values, but it should be equal to the mean of these values t for a given x. And for this, we can also set that we have more of a vector representation, where we have the probability of the set t of target values is given a set of input vectors, so not just one input vector, but all of them, the weights and the precision of this normal distribution. As these t's are taken out independently, this probability is a product of this normal distribution, where for one, it is the probability normal distribution of achieving a given Tn for the, and here we have the weights multiplied or dot product with our feature vector phi. And that's our mean value, and this becomes our variance parameter. So we assume a certain variance parameter, for example, for a spread of our values t from its mean at that position. So again, what we can do is, in order to perform the maximum likelihood, we can perform make a logarithm out of this function, where we move the logarithm into the argument of the operator, and then the operator turns from being a product is a sum, and it's a sum of these individual logarithms of these normal distributions which were previously multiplied together. Here they are summed up. The logarithms of these normal distributions are summed up together for all the Tn's. And then the logarithm, as we know, will be represented by the n half ln beta, if the precision is the parameter, then n½ ln 2 pi minus b times 1/2, and then the sum of the squared differences between the target values and the feature vector containing the basis functions, scaled or weighted by the particular weights. And then if we are performing the log likelihood derivative with respect to W, so which means that we will be looking for the value where the derivative is then equals 0, which means that we at that position we will have the maximum likelihood, then our derivative of this function will turn out to be with respect to W is this term here, because the derivative is deriving the terms for each element of the sum, and the W element associated with this somehow scaling factor is the variable which we are deriving, and therefore it is like W in the squared. Therefore we perform first that this squared is turned into a not squared function but a linear function, and then times the inner derivative where we will have this phi xn transpose outside, and that should be equal to 0. From this we can define our formula for the least squares for the maximum likelihood, where we can see that the sum of the Tn times the vector phi xn, the feature vector, is equal to the weights and the multiplication of the feature vector with its transpose. So how did we come to this result? Just if we would go to the slide back, we can see that the phi xn transpose was a multiplier of a sum or difference operator in the brackets, and we are multiplying the individual terms, and then we are putting them on each of them on one side. So now what we want to really do is to isolate the W, because we want to find what is the maximum likelihood of W's to fit a particular sample points given a basis functions which are here. And we can see that we have this transpose here, which is forming here in particular. So this will be just a forming just a row vector here. However, here we will have a formulation of a outer product. However, we can see that this if we put this sum to the other side to isolate W, then we will realize that it is in fact a dot product between the feature vectors and a set of feature vectors, not on for each data point, and it is inverse multiplied by this phi transpose times the scalar t. Now here the scalar turns into, because we have all of these target values together, into the vector t. So this is the formula for the linear for the regression of a generalized formula. So this could be linear regression if we have the linear basis functions, or polynomial regression if we have polynomial basis functions, but pretty much any other basis functions could be used as well. If we study this structure here, we can realize that this phi transpose phi powered by -1, so inverse times phi transpose, is in fact something called pseudo-inverse. So it is kind of a function which is, or actually it is a matrix, which is somehow pseudo-inverse to the matrix phi. And what is the matrix phi? Matrix phi is the so-called design matrix, where we have our, in the columns, we would have our different feature vector functions, and in the rows we have the individual data points. So it has n rows and m columns. And it is called a pseudo-inverse because if the phi would be square matrix, so it would be an n by n matrix. Like, for example, we can imagine that we have the feature vector consists of polynomial basis functions and the polynomial up to the polynomial degree n-1. So in such a case, our design matrix will be n times n design matrix, and it will be a square matrix, and it will be also invertible matrix. Therefore, we will have, unless we have several times the same sample point at the same location. But generally, we will have a square matrix, and this square matrix, if it's invertible, then it will be, the pseudo-inverse will be actually equal to inverse. Why is that the case? Well, just look here. If we can perform this inversion here, what will be the result? So we will have these two will be, the order will be replaced. So we will have the function of phi inverse, if we are getting rid of this bracket, phi inverse times phi transpose inverse times phi transpose. So the phi transpose inverse times phi transpose will form identity matrix, and we will be left out with the phi inverse. So for invertible matrices, the pseudo inverse will be equal to the inverse, but it will serve as an inverse even for matrices which cannot be which are not invertible. For example, we could be all interested in expressing the maximum likelihood estimation for the bias term. So in order to do that, we define our data error function, which is the 1/2 of the sum of square differences between the input output target value and the weights multiplying our feature vectors. However, we can explicitly take out the VW0 weight and perform derivative with respect to this W0. That will lead to the fact that we have here it will lead to 2, so we will cross out this 1/2 here, and then it will also lead to the fact that there will be a -1 here, so the whole thing will be multiplied by -1. Therefore, we can take out the W to the left-hand side and keep it on the left-hand side, and then put all the other values on the other side, and we will have the equation which will be related. So we basically take the sum of this Tn vectors. Then we will have the n times W0, because n times W0 here, and then we will have the sum of these terms here, and that we will put on the other side, and we will divide by the n, so that the n which would be associated with the W0 by taking out from the sum, we divide by that, and we see an interesting outcome here, that this term here is in fact an average t, and this term here is an average phi, and we can see that our W0 can be expressed by calculating the average t and subtracting from it the sum of weight coefficients with the average phi coefficients. If we would like to find out the maximum likelihood for the precision, for example, we can perform a similar operation as we did before and try to find the inverse of the precision by finding the variance, which is the sum of squares normalized. We are already quite familiar with the least squares method. However, this time we have added this generalization of having the feature vector, which makes the intuition a little bit more abstract. Perhaps a help could be to think of a geometric perspective on the least squares. So imagine that our feature vector and our vector t, the target vector t, lie in some kind of n-dimensional space. This n-dimensional space is in fact spanned by the axis with values t1 to tn. So for each of the target values, we have one axis, and that one is spanning having an associated value t1, t2. So these are scalar values in the n-dimensional space, which are finally defining us the vector t. Imagine if we, by pointing here on the geometric representation, we have here a so let's say this is a three-dimensional space, and we can see that in this three-dimensional space we have somehow one vector here forming this one or maybe two vectors are forming this one axis, or it's a linear combination of two axes. Then there is another one which is taking it somehow higher above this kind of a plane which we have here. And we can see that with the green we have here our target vector t as a linear combination of the axes which are spanning this vector in this n-dimensional space. Then, if we have the basis functions phi j if they are, we have them represented here as for different x vectors. We can see them that they are spanning vectors in this space. So imagine that you have a set of these input vectors from x1 to xn, and the entire phi j of x1 to xn is within this n-dimensional space, and it is there are the components of this vector phi j. So for phi 1 x1 is one component, phi 1 x2 is another component, until phi 1 xn, that is one vector, like this phi 1 here. Then we have another vector phi 2 with all the components, with n elements of phi 2. And so these are the vectors. And now we have here, imagine these are the vectors, and our y can be a linear combination of these vectors. And this linear combination is achieved by the w's. The weights, the w's, will achieve us that the linear combination of these two vectors could be, for example, this vector. Now, if the n is bigger than m, so we are not really overfitting, our number of samples is smaller than the number of the feature vectors, let's say a polynomial degree functions. In such a case, the phi j will be spanning vectors, will be spanning a linear subspace S of m dimensions. So it is a subspace of the space N. It is embedded in the space N. And therefore, anything what is within this linear subspace S here can be achieved by a linear combinations with these weights W. And any point. However, if our value vector t is out of this subspace, we can never really reach exactly the same value. We will always be somehow trying to be as close as possible. And this vector y, which we are, the vector y is therefore also an n-dimensional vector which exists in this subspace S, and therefore its nth element is simply the y value of xn and the weights. The weights are the same constant for all sample points. However, the xn is varying the input vectors. And we can obtain it as a linear combination of these phi j functions, feature functions. Now, if we want to minimize the sum of squares between the sum vector y and the t, then while the y is constrained to exist within this subspace S, then we will be bringing the y to have the minimal Euclidean distance, or its square, to the point t, you could say. And that means that y is actually an orthogonal projection of t onto subspace S. So we can see this beautiful geometric explanation of this linear regression here, where if we have generally a smaller number of feature functions than the actual samples, then we will stay within a certain constraint space, and this constraint space will have some points, maybe one, which is the closest to the value t, and that will become our maximum likelihood estimate of the least squares, using the least squares error measure. Now, we do not need to have in the least squares only the option of having the kind of a batch processing like in the maximum likelihood approach. There we are using all the data points in order to estimate the weight values W. But for maybe very large data, which do not fit into memory, or in case of like streaming functions, streaming values which are coming from measurements at a certain points in time, we will need some sequential solution, some sequential learning. We already had the sequential learning mentioned in the previous chapter on probability distribution, where we had this Robbins-Monroe approach. And this is something fundamental, which leads to definition of the so-called gradient descent method, which is at the heart of any optimization for machine learning. So if we have our error function, it could be decomposed into a sum of error functions where the E error function is equal to the sum of error functions after presentation of pattern n and all the patterns before. And then we can perform an optimization of or estimation of the vector W in an iterative fashion. So we are having the vector W, which is the set of the weights which we are weighting our feature functions with, and it is the next iteration is based on the vector W from the previous iteration minus some eta here, which the eta stands for the learning rate and doesn't have really anything to do with the eta which we were talking about in the past lectures. It is just the name of the learning rate, but it has a relationship to the function an in the Robbins-Monroe, where this function was, for example, set up that it is gradually increasing sequence of numbers. So that could be also the learning rate here, but it doesn't have to be. The learning rate can also stay and be constant for at least some set of iterations. And this learning rate, so which basically defines how much of this gradient of error is being used to adjust the weight W, is used in as a product with this change in the error function. So if we have a certain W and our error function has decreased, then we are generally having a smaller contribution to the weights than if the error function will be increasing. Now let's have a look at what it means for the least mean squares, this error function. So simply, we need to calculate the gradient of the error function with respect to the nth error associated with the presentation of the input vector xn forming as this feature vector. But if it's a derivative with respect to w, we can see that it is again having this form where this was squares, and then we performed the derivative, and then this derivative led to this, that it was no longer squares, and it is multiplied here by the feature vector. Now, therefore, we are calculating these values. So this is some kind of, if you look at this is a scalar value. This is a scalar value. Here, the dot product with the weights from the previous iteration transpose with the feature vector of the xnth sample will form as a scalar value, which will be somehow close or maybe not so close to the value of the target value which this function y expressed here should represent. And then once this is calculated, this how close these two are times this learning rate, this is scalar to the feature vector, how much this feature vector basically contributes to the change, to an update of this weight vector here. And gradually, with these updates, our weight vector, weight coefficients will be updated so that they are leading to the least squares representation, like if we would have with the maximum likelihood approach. The difference here is that here we are not doing it in the closed form solution way, but we are performing an iterative update in this sequential learning setting. So this is an example of the gradient descent, and which we can use in our linear models for regression. Now, if we look at the regularized least squares, we just are adding to our error data term also the lambda times the error which is associated with the w vector. As we said before, we want this w vector to be ideally small, and we can see that we can express it by having the least squares or the squares, sum of squares, combined with the magnitude of the w. Now, this also can be seen as has a relationship to the constraint, and the constraint would have here like something like some value. So this should be smaller than some value, so there will be some minus and the value. But here we do not have that part, which stands basically for 0. So we want to have that these values as possible close to 0. And the generalized formula for the closed form solution of our weight vector is very similar to the previous case with the feature design matrix here, but the design matrix and its pseudo inverse is slightly modified by this diagonal matrix where our lambda, the parameter associated with the regularization, is forms a diagonal matrix with the values on the diagonal all of the same value. So this generates us this slightly modified pseudo inverse, and with that we will be obtaining in a closed form solution the values for the vector W. We already had that for the linear regression case in the chapter 1 on the slides. Here this is generalized solution where we here have the design matrix, which is for arbitrary matrices containing feature vectors such as polynomial degrees or the Gaussian or the sigmoid or the 10H or the Fourier or wavelet. And then with this formula, there is practically no difference. So whatever the design matrix has, the weights will be calculated based on that, but the general formula is in some sense independent of which features are being extracted from the input vectors. However, we have been previously using the vector dot product, which here in the regularized form, where the dot product was basically a squared form of the weights. So the weights would be small, would be pushed to be small, but somehow they are associated. This regularized penalty term is associated with the square of the vector. But we do not need to have, so here we have a more generalized representation of it, where we do not really have only a necessarily squared. We have here Q, which can be expressing a different relationship and not only the squared term. So you can see here that there could be different q's, like 0.5, so we will have a square root instead of square. We will have q equals 1, so we will have like sum of absolute values of these individual weights, and then we will have 2 or 4. We could have arbitrary values here. So, and in this particular setup, in fact, while the quadratic is very popular, the other one, where the q is equal to 1, is also very useful. It's called lasso, and its basic benefit is that it will lead to a much sparser representation of weights. It will lead to the fact that many weights will, in fact, the coefficients will be equal to 0. And why is that the case? So here again will help us the geometric intuition to comprehend that. Let's have a look at this lasso regularization where the q is equal to 1, the exponent term, and we can see here that we have here some kind of weight function where the weights are, this is the data term, where these weights would be kind of, this will be the ideal value for the weights. However, if we only consider the data point, however, with some weights we are having some bigger and bigger error, because we are having a regularized term, and we need to somehow come up with a sum of these two error terms, which is in sum minimal, not individual. One of them is small. And we can see that the regularizer, for example, for a given value, and here we have again the naming convention of eta. If this should be smaller than eta, it means in the squared sense that we are somehow in the circle which is smaller than eta here, or equal to eta on the circle. So here we will have some values of the weights, and we can see that both the V1 and the V2 will have some non-zero value. However, if we have the lasso, we will have the values will be like the q equals 1 forms us a certain kind of a diamond shape of this value, where the sum of these weights is equal to a certain eta. So you can see here, this would be the eta for the V1, and in that case, the V2 will be 0. Maybe here we have V2 is equal to eta, V1 is 0. And here we have a linear combination between the V1 and V2, but all of them are non-zero, but we have this straight line here where the value, the sum of the V1 and V2 is equal to eta. And as it is in the absolute values, we will form this kind of a diamond shape by this lasso regularization. And that will lead to the fact that our weight error term will be meeting our regularizer error term on one of these apexes, which are kind of sticking out compared to the perfect circular representation of this regularizer error term, which comes from the squared representation of the regularization. We also have the naming conventions if this q is equal to 1 as the L1 norm, and if we have the Q2 here as L2 norm. And this L1 norm, we can see, here, that it leads to this meeting the regularizer error at the apex of this kind of an n-dimensional diamond of the dimensions which the weights are associated with, and that will mean that some of them of these weights will have some value, non-zero, but many of them will have zero value. Like we can see here, the W1 has a zero value because it met at this location of the data error with the regularizer error. Also, so far we have been discussing the case where the t is a scalar. So we calculate the function of an d-dimensional vector x, and then the outcome is a scalar. But we can have as an outcome also a vector outcome, and then we can have, for example, the vector, the t can form a vector, which could be bigger, so could be k-dimensional vector. In such a case, we will have our function y we are looking for will be in fact a vector valued function, and it will be based on the multiplication of a matrix W transpose with our feature vector. and this weight matrix will be a M times K matrix. Previously, it was an M-dimensional vector, but now as we have, say, K outputs, maybe 3 outputs, it will become an M times K dimensional matrix. So, for example, for an isotropic Gaussian, which has the same precision for all of its dimensions, we will have that the probability of a particular tuple of T given an vector X, the matrix W beta, can be governed by the normal distribution, where we have the mean is expressed as this multiplication of the weights matrix with the feature vector, and the covariance matrix is expressed as with the reciprocal of beta along the diagonal. So if we would like to set up a maximum likelihood estimation, then we will have the probability of a T, which now the T will no longer be the set of different values of the output value, which is then organized as a vector, but we have several output values per each T itself is a vector. So we will have a matrix N times K. And then the X is also a matrix, W is also a matrix. And then we will have a precision here for if we are modeling with the normal distribution. And we are again performing the logarithm of this function to obtain the instead of multiplication, a sum of this logarithm of the normal distribution with the Tn. So this is just one tuple of the T associated with the outcome of the multiplication of the W transpose matrix with the feature vector. And for that is the mean, and then we will have the like a multidimensional mean here, and then we will have the diagonal isotropic type of Gaussian here. Now again we can see that the NK is now that we no longer have here only K, but we have here NK divided by 2 associated with the precision and the factor 2 pi. And then our square term is having again the square term, but here we have a difference not between a scalar, but this multiplication doesn't create a dot product anymore. It generates us another vector. So we have here a subtraction of 2 vectors, and therefore in order to have an error out of this vector is squared. So its size, its magnitude squared will be the scalar output of this error term. And then the maximum likelihood W matrix will be obtained again by the design matrix pseudo inverse multiplied by the T matrix. So for each target variable, it will mean that we will have the column of the WK calculated in the usual way, where we have the TK. So this is just for one coordinate of this tuple T, as this will be over the K or N data points. Now let's move our discussion into a method that can give us an insight about certain model parameters. We have been looking into the various ways how we can perform regression, and in some cases we can have a good regression given some model parameters, and in some cases we can have a bad outcome, maybe overfitting, or the model is too simple to represent the complexity of the underlying data. So the model selection, let's say the degree of a polynomial with the choice, definitely strongly influences the outcome of our regression approach. Therefore, it is important to choose a right one. But which one is the right one is the question. And the same holds, for example, for the regularization. So we have a regularization term, that's fine, but that one is always weighted by this term lambda or lambda half. And what should be the value of lambda? It's a question which would need to be answered. And we have here, we will be discussing the so-called bias variance decomposition, which will allow us to see an insight what is a particularly suitable, let's say, lambda or model parameter setting for an ideal best outcome of our regression process. So let's start with first some recapitulation of various aspects which we have obtained already in chapter 1. First of all, imagine that we had this regression problem where we had this sine function before, and this sine function was generating us the sample points, but these sample points were also affected by some noise, which was distributed by normal distribution. Now, this sine function is actually generally an unknown function we are trying to estimate. In this synthetic case, we know that it's a sine function, but this unknown function, we can define it as the hx. This function hx is the one we are looking for. We want the yx function to be actually reaching the value of this unknown hx function. So if we have the polynomial functions, we want that this polynomial function is as close as possible to this sine function, which we had at the beginning for generating as this synthetic data set of noise influenced samples taken from the sine function. So we don't know this function. However, we know its optimal values for a given x is in fact the expected value of the t's. So imagine for a given x, like we have here in this graph, like it was in the chapter 1, we have here a particular value x, and along this x we will have several sample values distributed, and now we just want to find out the ones which are like we want to find out what is the expectation of these values t for a given value x. So that will be the mean of these t's for a given value x, and that will be forming the expectation. So this is the best optimal prediction of the regression function h of x. But we do not really know the function. We only know its value at particular position x and at some other position x. For given x, we know its value, but we do not know its form. We know the outcome values, and we can form a pair of input x vectors and the output target value, but we do not know what is the function, that the function was sine, in fact. And we want that our values y are getting as close as possible for a given x to this regression function hx. And as we can see, as we have chosen the basis functions being the polynomial previously, then we will never meet exactly the perfect match with the sine function, but with some cubics or cubic curves, we can get reasonably close. So now let's have a look at the solution function y of x. If we want to generate an error term, we would be usually dealing with this square term yx minus t square. So this is the squared square, which we also can use for defining the loss if we are performing the learning of our function y. And the function y is in fact the multiplication linear combination of some basis functions weighted by the coefficients from the w. So that is forming our function y. Now let's change this term slightly, and we just inject here a term which is together equal to 0, and which is minus hx plus hx, and in the square term. Now, if we multiply this out, where we observe this as one term and this as another term, we will have a term yx minus hx squared plus, and then we have the 2yx minus hx minus t, and then the third term will be hx minus t squared. We can see it clearly how we can decompose this square into these three terms. Now, one term here is basically telling us how far is our polynomial function from the sine function, and then the other term here is telling us how far is our sine function from the individual values t, which correspond to that at that position, which in fact leads to understanding the noise, the inherent noise in this underlying process, which we are trying to match. And then we have the third term here, which is the cross term. If we are using this function for defining our loss, the loss can be defined by as this. And what we typically want to do in like the decision theory, we want to minimize the expected loss. So if we want to minimize the expected loss, which is here, then of this square term of the joint distribution of x and t, then we are interested here. This is our expectation. So this is our function, the loss, times the corresponding probability distribution. Now we have injected into this square term, as before, this hx and minus and plus, which together is equal to 0, but we want to use it for decomposing this integral, or this integral of the loss, into some other terms. And so therefore we can see that the first term is the yx minus hx, and although this is a double integral over x and t, there is no t here at all. Therefore we can just integrate out the t and just have the single integral over the x, which is then this function. So it's an expectation of this with respect to x, px dx. And then we have the cross term, which is here associated just with the x, and the other part is associated both with x and t. And then the last term here is the um, uh, um, the term which is measuring somehow the inherent noise of the phenomenon, where we see measuring the squared of the regression function from the individual output target values. And here we have both x and t variables, so we have a double integral. Now, the interesting aspect when observing this loss expressed as an expectation for the decision, so minimizing this expected loss, we can see that this term here has the term which has the regression function minus t. And while this is not zero for one term, for this is actually, as this is an expectation of t, so there will be, and this is not a square term, so sometimes it will be, the error will be slightly above, slightly below, but the expectation will lead to the fact that the average of these t's for a given x will be actually equal to the regression function. So this term, in fact, will be equal to 0, which will lead to the fact that this entire integral is 0, and also this term is 0. So the entire cross term here will become 0, and we have only two terms: the term associated with the difference between our function, which we are defining, and its weights and the feature vectors, and the regression function, the underlying function, and the inherent noise in the phenomenon, measured as the difference between the regression function and the values t. Note that although we have this same term here and here, we define this as being equal to 0. This term is not equal to 0 because this is actually squared, so this will be always positive, while here it will be sometimes positive, sometimes negative, and overall on average it will be this term will be zeroed out, while here we will have only a sum of positive values, or integral of positive values, which will not be cancelling itself out. In other words, the error here in this signal or in this phenomenon has a zero mean, and that leads to the fact that this term will be 0. So okay, so our expected loss will have this formulation where we have this term, discussed its meaning, and this term. Let's have a look at it in more zoomed in one more time. So we have this one term, the square difference between our function and the underlying unknown regression function, and choosing the optimal yx will be minimizing the expected loss. And this part is the intrinsic data noise, which is a minimal achievable value of the expected loss. So we cannot have a smaller expected loss than this term, because this is actually the kind of the noisiness of our phenomenon, which we are trying to estimate. So now imagine the following thought process. We have imagined that we have a huge unlimited data pretty much, and out of this data, which is characterizing the same phenomenon, we are taking number of data sets, and they are all of the size n, so they have all n sample values taken from the same probability distribution. So, and for each of these data sets, we will learn a particular value y, which we can obtain through the closed form for example, of the maximum likelihood. And then once we have this function, we are looking at this term, which is the square of our learned function from the underlying unknown regression function. Now let's now take from all the data sets, we calculate from these y's, and we will take an expectation of this y. So here is an expectation of y, which is an average y function. So if we have a function which is characterized by the weights multiplying the features, then we will here have an average weight representing our function y. And we again do the same trick that we inject into this squared term, which was already taken out of another squared term previously. We inject there this expectation of this average y minus and plus, and then we have our regression function. This again we can decompose into three terms. One is the term which is measuring the y from its expectation, which in fact is a variance. Then we have a cross term, and this cross term again has the property that this if this is put as an expectation and this is expectation, these expectations are again having an error. There is an error which has a mean 0, and therefore this and as an expectation will be canceling each other out. We will see that. And there is and then we have the third term, which is the expectation of this y minus the regression function. Now, so now we put this square term into expectation. So the expected loss of this term is equal to, and that is equal to this one term where we have this average y from all the data set, this expected y minus the regression function that measures our expected distance from the regression function, and then overall bias of this choice of this function. So, like for example, we have a polynomial function, and this is a sine, and there will be some difference just because we have a different basis function. This is polynomial, this is sine, so there are two different basis functions which leads to a certain difference. And then we have this other term, which in fact is the variance, as we can see by the definition, expectation of the distance from an expected value squared. And then we have the cross term, and this cross term, as I said, is equal to 0 because the mean error here is the mean of the error here is 0. And if we take out that cross term, we can see that this expected loss from these several datasets can be represented as the one term, which is called the bias term, which measures the difference between our y on average from the regression function, unknown regression function, and the variance of the y from the average, which basically tells us how dependent is the y on the choice of the values in the data set. The bigger this is, the more dependent the choice of the data is, more dependent this function is the choice of the data. And the smaller the variance is, the less the variance is in the or less influences in the choice of the subset of the whole data set. So once again, the bias represents the extent to which average prediction over all dataset differs from a desired regression function, and the variance measures to which extent solutions from different datasets vary around their average. So now we put it together to the expected loss, and we can see that we have here the one part which is the bias term, another part which is the variance, and then we have the third part here which is the inherent noise. So we have these three parts, and we cannot do too much with this one, but these two are giving us an insight about the suitability of a certain model, whether this model is good for our regression goal, or it is not very suitable hyperparameter. We can see it here on the case of 100 different data sets with each of these 100 data sets has 25 data points, and it is the data, the function y is modeled with 24 quotient basis functions. So not with polynomial functions, but with the basis functions. And the whole model is a regularized least squares with the parameter lambda in our as influencing the degree of regularization. And we can see here that this particular regularization value, ln lambda is 2.6, relatively large, will lead to an over-regularized effect. And we will see that while there is a relatively small variance, so these individual curves of this function y for each data set are not changing too much. There is no big difference from some kind of imaginary average. Actually, the average is shown here on this plot, this red curve. This is very small variance, but it has a very large bias because this is our regression function, the sine function, and this sine function is not matched by our solution function very well. So the bias will be high here and the variance will be small. And the overall goal is to find settings of this hyperparameter lambda such that the bias term and the variance are both somehow well balanced. So none of them is too small at the expense that the other one is too large. Here it's 100 datasets, but you can see here only 20 curves just to make the drawing a little bit more easy to read. Now we change the lambda, and we again calculate from all these 100 datasets the y's, and these y's are plotted here. These are all the functions which we come up with for different datasets of these Gaussian basis functions, which are forming us this set of y's. Now this set of y's is a little bit, the variance is a little bit bigger. So this is our average y, and it's the variance. We can see it's more. It's generally broader. This band of functions, but the bias term is very small. So we have increased a little bit of our variance, but we have decreased substantially the bias term. And this is by changing the lambda, ln lambda is equal to 0.31. Now for the third term, for third setting, we have again changed the lambda in the regularization parameter, and we had 100 data sets, and we calculated the y's out of this, and we can see that these y's are now generating us a lot of a lot of big variance. So there is kind of somewhere here the center, this red curve, but the variance between the individual y values is very big. And however, the bias is almost zero. So here we do not have, this is again leading to some unbalanced situation where at the small bias term we have the costs of a large variance. So now let's have a look at what could be considered an ideal setting and evaluate it in some kind of systematic way for this hyperparameter lambda. So we can see that we have this average value y here, which is simply an sum of our y's for a given x and divided by the set of all y's. And then we calculate the difference between this average y and the regression at particular data points. We do not know this function h, but we know the actual values t, which are represented here by this function. So this will give us the bias term, and the variance will give us the difference of each individual y function per each data set from the average across all the data sets. And we can see the plot here where we have the error of the variance is decreasing with increasing lambda, and but the error by the bias is at some point increasing from a certain lambda or ln lambda. So from the ln lambda around 0.3 or 0.5, this is going to be high up, and we want to find a place where the sum of these two, sum of the blue one here and the red one is equal to some ideal value. So here at the crossing, this is probably the ideal value, which leads to the minimal value of the sum of these two, or somewhere here, maybe a little bit earlier will be the combination. And this corresponds to the test error. So we have a corresponding error from like a test set, and the test set will tell us how the error is changing with respect to the lambda, and we can see that this bias and variance error together is when it's balanced, it corresponds to the lowest value at the error at the test error as well. So that will be a good choice for the lambda for this or ln lambda for this particular setting of regression. Solving the problem of linear regression with maximum likelihood estimation leads to the problem of model selection. We do not know which model to select, whether it's a simple one or a complex one is appropriate. And this can be maybe tackled by several approaches, such as, for example, cross-validation. But this would require training of several models, and will also lead to some partitioning necessity of our data. Alternative approaches could be that we have a certain validation set and test set, and these can be used for assessing the model suitability. However, this leads to shrinkage of available training data, because we need to have some data reserved for the purposes of the model selection. Now, if we turn to a Bayesian treatment for linear regression, we will this will lead to the fact that we will be not having anymore the overfitting as a problem. And we will also see that Bayesian treatment can lead to a suitable model estimation without the necessity of splitting the data into several parts and reducing effectively the size of the training data. So let's have a look at how we construct the Bayesian linear regression. So here we have the likelihood function, which where we have a certain input, which is now captured in the design matrix phi. So the input vectors are represented by the feature functions. Then we have certain weights W, and then we have a certain precision or standard deviation or variance, which is attributed to the noise. And this is therefore a normally distributed data points around a certain function y, which is having the form of the phi, capital Phi matrix, design matrix, times the weights vector. And it has this is the mean of the normal distribution. And then we have the isotropic Gaussian around with the covariance matrix equal to the identity matrix multiplied by the inverse of the parameter beta. If we now formulate this probability distribution in its algebraic form, we see that it is an exponential function where we have a square term with respect to W, and this also can be then represented as a set of individual data points and the feature functions, as we can see, and the output vector entries as follows, which is a product of the individual normal distributions associated with each data point given the same weight vector. Now, the weight vector has a prior as coming from a normal distribution with a certain mean m0 and the standard deviation or variance equal to s0. So if we want to now define the Bayesian treatment, we will define the posterior, which will be given by the multiplication of the prior with the likelihood function. And we can also note that the likelihood function has the term phi here, which in fact is a function of or better to see it in this normal distribution where the vector W is multiplied with this matrix, design matrix phi here, and therefore it is like we can see that this W, which is the same W as this W, here this is a linear transformation of the W by the design matrix phi. And therefore, we can see how the posterior structure will look like on the next slide. Before we can recognize the structure of our posterior, which will be equal also to a normal distribution of weights given a mean and a certain standard deviation of the posterior, we will see the way how we can find the mean and the standard deviation, or the variance actually. So if we look at the conditional Gaussian from the chapter 2, we realized that we had some px probability distribution where the x was given by some mean and some variance, which was the lambda precision matrix inverse. And then we had also a conditional Gaussian, a y given x, where the y was in fact its mean was given by a linear transformation of the random variable x, where we had ax plus b, and it had its own precision matrix capital L, expressing the variance as its inverse. And also we had the out of these two, we can both express py, and we can also express px given y, so the conditional Gaussian in where the x is a probability of x given y, and that we have found that the mean is given by this complex formula here, and the variance is given by this term. If we go back to the chapter 2, we will realize that we have obtained these results by completing the square, and this information shows us that this is in fact the terms inside the bracket are in fact the precision matrix of this conditional probability distribution. Inverse makes it the variance matrix, and the mean in fact is expressed as this term, which already includes the variance inverse and the mean. And in order to get the variance inverse out, we multiplied with the variance, with the covariance matrix here. So now, if these are the variable names which we have been using before in expressing the conditional Gaussian. Now we are in the linear regression, but we can recognize that the x can be is replaced with w, with our weight vector. The mu here is the prior m0 mean, and the precision matrix capital lambda is actually, or inverse, the variance is actually equal to the S0 variance matrix of the prior. Now, from the conditional Gaussian, the linear transform Gaussian, we can see that the y is our output vector t, and the a is actually our design matrix capital Phi, b is equal to 0, and L is equal to the precision matrix for this conditional Gaussian, capital L is equal to beta times the identity matrix. So now, if we take this and replace it into our formula for the Mn and Sn for our, so here the pxy, we can see the x is w and y is t. So pwt, our posterior, is again a normal distribution with some mean and some variance covariance matrix. Now what is the covariance matrix? Let's have a look at that first. So the covariance matrix here is, so let's have a look at, so this is this here inverse. So we have here also like if we now do this inverse, it's like what is here inside in the bracket. So it is the capital lambda, which we see that it is S0 inverse, and then plus AT transpose. So this is the design matrix transposed, L, which is beta times identity matrix, and again A, so which is the precision, the design matrix phi. So if we slightly reformulate it, put this identity away and put the beta in front of the term, we will have the formulation for our precision matrix Sn, which is this term. Now, in order to find out the mean, we simply have the precision matrix inverse, so having the covariance matrix here as we have it here in this result which we obtained earlier, and then times this term here. And this term here is now, again, capital lambda is S0 inverse, and then times mu, which is in our case M0 plus, and we have here A transpose, which is our design matrix phi transpose, and then we have the L, which is beta times identity matrix, and then we have the Y minus B, which is T minus 0, so it's T. And that is our mean, which again we can remove the identity matrix here, put the beta in front, and we will have the resulting formula for our mean and variance of our posterior distribution of our Bayesian linear regression involving a prior and a likelihood function. Now, and this is already normalized because it's a normal distribution. So it's not only proportional, but it's equal to that. So we end up with a Bayesian theorem giving us the posterior distribution of the parameters W, which incorporates the prior together with the likelihood function, which is representing the observed observations. It is worth analyzing this outcome a little bit for the posterior probability distribution for our weights W. So what is the MN, the mean of the posterior distribution? In fact, this is the maximum a posteriori estimation for the weights W. And then if we will, for example, have a prior, which will be the variance covariance matrix will be S0 A reciprocal times the identity matrix, where the A goes to 0. So this will be a very, very high number, very high covariance matrix entries on the diagonal. Then that will lead to the fact that our term for Mn will be actually going to the linear regression term, and it will therefore lead to the maximum likelihood estimation for the W. So we can easily come to this result if we observe the posterior precision matrix. So here this value will become 0 for A going to 0, and therefore we will have only the part associated with the beta and the design matrix. This part here, as you remember, is the S0 or S0 inverse, to be more precise. and this term will therefore disappear. And for our precision matrix, we will have only this term. And in fact, for our inverse of this, we will have the same term, but instead of beta, we will have 1 divided by beta. And of course, this matrix multiplication of phi transpose with 5 will be inverse. Now, if we now look for the Mn, it will be this part, which will be 1 divided by beta, and this part inverse. And then for alpha, then for the rest of the Mn part, this will be the part which will be remaining, because we have for the Mn, so this is like, it's the Sn, which is this part with also the beta, but that is then cancelling out with the beta later. Then we have in the brackets the S0 inverse, which we already have also had in the previous case, and that is equal to 0. So it also removes the M0 prior, and then it only multiplies with the beta design matrix transpose T. So we end up here with this expression for the maximum likelihood estimation for the weights W. So, and if we do not have any data, we have only the prior, then we can also see that the Mn will reduce into the M0 because we will only have the non-zero first term, and the S0 Sn will have only the part of S0, and that one S0 and S0 inverse, which is in the Mn, will cancel each other out, and therefore the Mn will be equal to 0. Now let's have a look at the formulation if we have some suitable prior used where the probability distribution of the prior is again a normal distribution, and with the mean equals to 0, the origin, and then we have some isotropic covariance matrix governed by this reciprocal of alpha I for some constant value of alpha. Then the Sn is equal to alpha I plus beta, and then we have the phi T phi design matrix multiplication with itself, and then we have the Mn, the first term for M0 will disappear because the M0 is equal to 0, so we will have only the second term, and the second term will therefore involve the Sn times the phi T times the output vector T, where the beta has been then taken in front as the scalar. Now, if we have this probability distribution as a posterior, we can have a look what is the logarithm of this probability distribution, and we can see that the logarithm with respect the logarithm will give us two terms, which will be including the terms W, and one is the exponential term, which will result into the sum of the Tn minus W transpose times the feature functions of the input vector. So this is here now we have represented our normal distribution of the likelihood by its decomposed it into the sum of the individual data points, and then we have the part which is related to the alpha, and we can see that there is a term W transpose times W. we can definitely recognize that this term comes from the exponent of the likelihood, where we have the beta associated with the identity matrix as a covariance matrix, isotropic covariance matrix. And in fact, we have a very similar origin of this term, which is also the exponent of our prior. And here we had the covariance matrix multiplied by the term alpha, reciprocal of alpha. So for the precision matrix, it would be the alpha, or the covariance inverse, it will be the alpha, which will be coming as the scalar term, while the identity matrix between the W minus 0 and transpose and W minus 0 transpose will then be removed, and we will have just this term, which is the term representing the exponent in the prior, the square in the prior. And this plus this logarithm results into some constants, which we here aggregate into this term C. So we can see that this posterior log of the posterior corresponds to the sum of square error when we will be using the lambda will be equal to A divided by beta. Because if we set this to 0, then we can divide by beta half here, so we will have only or just by beta, and then we will have here the alpha divided by beta will become the lambda, and we see that it will be the sum of square error using the regularization term with the L2 norm for the W. Let us study the process of the Bayesian linear regression on a simple example. In this example, we will be having just a scalar input value x, and instead of some multidimensional vector. So we will have a univariate case, and also we will have a simple case where we will be looking for the corresponding weights to estimate a unknown function, where the unknown regression function f is governed or defined by the two parameters a0 equals minus 0.3 and a1 equals 0.5. So this will form a simple line, which will be the points will be more or less on the line, because we will be choosing the sample values between -1 and 1 as in a uniform distribution, and to this function we will be adding a Gaussian noise with a precision equals to 25, and for the prior, which will have its mean naturally at 0 for the weights, the precision will be equal to 2. So if we just first will be visualizing the prior probability distribution, we will see a Gaussian where this dark red is the highest probability, and all these rainbow colors are indicating a Gaussian lobe of lower and lower probability, going more far away from the point 0, 0 here. Now, if we have just a prior, and we are defining the drawing some weights W from this based on this prior. So here we have the W0 W0 weight, and here we have the W1 weight. So this is the as we can see, the highest probability will be for the values 0, 0. So we will have a constant function which is aligned with the axis x on an xy plot. Now there are also other possibilities, but generally we can see that here we go, the probability distribution, which is kind of still significant, goes between -1 and 1. So the bias will move our line by to -1 and 1. So the line, if it will be horizontal lines, there could be like the minimal value will be here, the maximal value will be here, and then we have so it's like a bias from the point 0, 0, and then we have also the W1, which in fact is this this term here associated with x, and we know that this is the tangent of the angle spanned between the line and the x-axis. So, and this angle is between, again, -1, 1, where 0 tangents is 0 degree, and 1 tangents corresponds to 45 degrees, and here we have -1, which corresponds to -45 degrees. So we will have basically here from the prior coming the lines which have the angle ±45 degrees with some reasonably high likelihood, with the 0 degree with the highest likelihood, and with the bias also -1 and 1. So this is how our lines, which will be generated based on our prior probability distribution, will look like. Now the line -0.3 plus 0.5x will be approximately, so -0.3 will be starting from this point, and 0.5 will be something between 0 and 45 degrees. So let's say it will be a line which will be something like this, maybe. That is the line we are in fact looking for. But of course, the input values x, or for the target values, will be also influenced by the added Gaussian noise, governed by the mean determined by this particular value, and by the precision beta, or by the variance 1 divided by beta. Now, after we observe one data point, so it's important to say that here we are looking at a sequential approach to Bayesian linear regression, and we can both use a Bayesian linear regression, which is in the batch mode, where we take all the data points at once, but we can also use it in sequential manner, where we will calculate a posterior out of likelihood and prior, which in the next iteration for the next arriving sample point will give us will serve as the prior. So after we have our zeroth iteration, let's say we have only our prior, our first data point is arriving, and this is this data point, which is for a drawn from -1 to 1 for x. We have a certain value, and this value is just above 0. So this is our first sample point. So we have, so the x is almost 1 and the y is almost 0. So that is our sample point, and that forms us our likelihood. So in our likelihood function, this will be the outcome. Now let's start observing it step by step. Our true value for our W0 and W1 is expressed by this cross, which is the -0.3 and 0.5 coordinate for this A from the generating function f. Now our W0 0 and W1 have this strange diagonal here. This strange diagonal here can be attributed to our likelihood function based on our one sample. The sample has the value of almost 1 and for x and almost 0 for y. So it's not completely, but for the sake of reading this outcome of this kind of a very sharp, let's say, a rich type of probability distribution, we can interpret it as 1 and 0, and we can go back and recall our definition of what is the maximum likelihood estimation for W0 with respect to the other weights. So that is, in fact, the W0 is equal to the average T minus the sum of Wj times phi j. Now the phi j average. So the T is in our case what? It is 0. That is the y, and then we have 0 minus, and then we have the Wj, which is the W1 times average of phi j, but that is in our case just the value of x, which is 1. So 0 minus W times 1. So W0 is equal to minus W1. And in fact, that is what we see here. So if the W0 is equal to 1, it will be equal to minus 1 for W1. And then for if the W0 is equal to 0, then the W1 is also equal to 0. So we see this anti-diagonal structure here formed simply by the relationship between our two weights, W0 and W1, in our maximum likelihood estimation. So we do not have only just one value. This is a probability distribution, and the highest probability is associated with this nearly anti-diagonal structure here, and for all the others we have substantially smaller probability. And notice that if we multiply this likelihood with the prior, which is this isotropic quotient, we will obtain this highly anisotropic quotient as the posterior. So our posterior distribution is still a quotient, as we can see with the highly anisotropic the covariance matrix, and our still estimate highest likelihood for W still kind of remains in the W0 and W1 equals 0, 0. So this is what happens with our posterior distribution after obtaining the first point. And we see that it has been somehow changing the transformation matrix in sense that it is an anisotropic distribution now, but as a line cannot be determined by a single point, the center here still hasn't moved. So now, so to the right position for estimates of W0 and W1, because a line can be estimated by minimum 2 points. So now let's have a look what happens in the second iteration. So this is the outcome of the first iteration, and in the second iteration we will have another point arriving for which we will estimate independently the likelihood, and we will take for the second iteration this probability distribution as the prior. So then for our second point here, which is minus 0.5 for x and let's say 0.3 minus 0.3 for y, This is again some sample point, so we see that the line will be going something like this, probably, and the likelihood here, which is generated, is generating us this type of highly anisotropic normal Gaussian distribution structure, where again our true parameters are somehow part of this likelihood function as in the previous first iteration. Now we can see that if we have here, this is now value minus 0.5, and we have this relationship that W0 equals minus W1, then if this is 0. No, so so in this case, it is the W0 is the average of t, where we are treating just this single case here, and for that it is again the x is minus 0.5, and this is equal to minus 0.7, let's say. So the W0 is equal to minus 0.7 minus y times minus W1 times minus 0.5. So this equals to a function which is minus 0.7 plus 0.5 W1. So we start if the W1 is equal to 0, then we should be somewhere for the W0 at the minus 0.7, which is also somehow true. And then we are if we are having the value, let's say for W1 equal 1, then we have minus 0.7 plus 0.5. It's something like 0.2, so we are here. So that is also corresponding to this likelihood function as we have devised the relationship between the W0 and W1. Now, also, what I forgot to say in the previous slide is that given this posterior, we can simply now draw our weights from this probability distribution, and so our weights W0 and W1 according to this probability distribution, and we will see that with this we can generate lines which look something like this, and they somehow all are intersecting more or less the first point. Now, if we are in the second iteration having this likelihood, and this likelihood is now multiplied with this, which was previously posterior, now it is a prior, we will see that we will suddenly have a posterior which is like very much localizing itself as a probability distribution more or less isotropic, and it is very close to our true values of A and B, which we used for generating the distribution already after arriving the second point, because 2 points, if they are not too much perturbed, are defining us the position, define us the line basically. Now, based on this probability distribution, if we are drawing samples for the W0 and W1, we see that all of these lines are more or less going reasonably close to both of these points. So we are already getting good grasp on what these points are. Now, we will be drawing more and more points in the next iterations. And here we can see, so this is still the second iteration, now we can see what is the outcome after the 20th iteration. So we see here that we have multiple points. We have 20 points. And in this case, we see that we have, again, the likelihood function defined for the 20th point, which is somehow, again, highly anisotropic Gaussian here. And then we have our multiplication with the prior in the with the posterior in the previous iteration. This is the second iteration, so it will turn into a prior for the third iteration, etc., until we are in the 19th iteration, and there the posterior will be prior for the 20th iteration. And after the 20th iteration, we have this as a posterior distribution, where we can see that our estimate in the center, absolute center here, we will have our W maximum a posteriori estimation, and generally this is the posterior probability distribution of our linear regression case, where we are estimating the line based on the 20 points. So this we can see how this Bayesian linear regression works, starting with the prior and adding data points in a sequential manner, and we can see how the likelihood is being generated and how does the posterior is generated based on the prior, and the likelihood, what data does it generate based on the samples, and then how it then turns out to be for the next iteration of this sequential setting. So far, our discussion has been concerned with finding the through the Bayesian approach the probability distribution for the weights W. So, and we obtained it through the through the prior and the likelihood function, and we obtained the posterior distribution for the W. But in practice, we are not really interested in the parameters of our function y, but we are interested in the prediction of given a certain set of training data. We would like to, for a new incoming data, to know what will be the output value and its associated probability distribution. So for that, we need, in the case of Bayesian treatment, the so-called predictive distribution, which is an integral over conditional distribution of the target variable and the posterior weight distribution. So here we can see that our predictive distribution of for the variable, output variable or target variable t, given the new x, and then the training set x and t, and then the parameters for the noise of the likelihood beta, and the parameters for the conditional distribution of the target variable beta, and then also the parameters for the prior variance or precision alpha. So, and that's equal to an integral of this conditional distribution of t given new x, and then the weights of our model and the precision beta, and this is weighted by the probability associated with these weights which we are using. So we are going over all possible weights, and we have always the posterior probability distribution associated with the weight vector, and we weight that with the probability of a t given those weights. So here we can see that we do not pick only one W set, like through maximum likelihood estimation or maximum a posteriori estimation, but we go over all W's, and we for each of these vectors we are associating with their probability distribution, which we are weighting this term with, and the outcome becomes the probability distribution of which is the predictive distribution for our target value t. Each of these distributions are actually normal distributions. So here we have the posterior, which models the weight probability distribution given its mean and variance, where the mean is the maximum a posteriori distribution for vector of W. And this is multiplied with the actual conditional distribution of the target variable, where we see here we have the value of the function y, which is simply the linear combination of the basis functions of the feature functions, where we have as an input the new input vector, and we have this is a linear combination made through this vector W, and this integral can be solved algebraically or analytically, and we will end up with this outcome, or it can be achieved by making certain observations and devising the parameters of this distribution. So one can see that this is a series of normal distributions which are weighted by some distribution which happens to be also normal distribution. So it's an infinite set of normal distributions, weighted ones. So it looks like a student distribution. However, in this case, we have a linear Gaussian here, because we have here the vector W from one probability distribution, and then this vector is just scaled by this feature vector or by the basis functions, and therefore the mean of this distribution becomes a mean of our weights, and then the scaled simply by this term phi x. So here we see that this is in fact our mean, and for our variance, we can see that it is equal to 1 divided by the precision of our noise representation, and then it is the product of the feature vector and the variance of the posterior and the feature vector again. And in fact, we have been dealing with a similar situation, however, in the multivariate case of Gaussian before, where we have the function of these two probability distributions and their joint probability distribution devised, and there we saw that for the probability distribution of the linear Gaussian, we had the covariance matrix for the Y multivariate normal probability distribution was governed by this formula, and where this term was the variance or covariance matrix associated with the probability distribution X, and this was with the probability distribution Y, and these were the matrices which were multiplying the linear term. So, and that leads to the conclusion that so this is the term of our covariance matrix of the distribution of the conditional distribution y given x in that case. So we can see that that is in fact the L is in fact the beta, or L inverse becomes the one reciprocal of beta, and this term we can see that it is the multiplier of the mean on around the posterior variance, which is from this linear quotient, the first distribution x. So we can see that multivariate case, which we already on linear quotient, which we already discussed, nicely maps also to the single variate case, and we can see the outcome here. So in total, this is the predictive distribution of our Bayesian treatment of this linear regression problem. Let's show the predictive distribution on an example of this sinusoidal data, which we already were dealing with in the chapter 1. And here, in this case, we will be using the linear regression to, or the regression using linear models to estimate the output value t given a new value x. So in this case, here we are representing our data by 9 Gaussian basis functions. So this is no longer a polynomial regression, but it is a regression where the basis functions are these localized Gaussian functions, which have a certain point x, and then we are measuring the distance from a certain centers. And these centers are somehow defined as parameters, which we do not have here explicitly present in this example. So, but what we can see here that how does the learning process proceed of this regression proceed when we are having an input of some data. So first we have the first point which arrives is a certain point for a given x value t. So here this looks like something like 0.4 for x, and it's equal to t is equal to 0. So this is the first point, and this is the value which is then associated with obtaining the likelihood, with finding out the posterior, and then waiting by this posterior for the estimates or probability distribution of W, the conditional distribution of for various values of x. So here you can see on this plot that we are estimating, in fact, for each of these values along on the x-axis between 0 and 1, we are estimating the values. What are these values? And these values will be equal to some probability distribution, which is the normal distribution with a certain mean and a certain variance, as we saw and we devised it on the previous slide. So the mean here is simply the weights of the maximum a posteriori estimation multiplied by the feature function of x. So now these are the 9 Gaussian basis functions, and they only are weighted with the one sample which we have. And that is giving us the mean value here of this distribution for each of these x. If we look at the variance is varying a lot between the x which are somewhat in the neighborhood of our point. So for the x which are in the area, let's say between around the 0.4, as we said, the variance is relatively small, while the variance of x more far away is becoming much and much larger. So we can see that the term of reciprocal of beta is becoming stays the same, but however this term for these Gaussian basis functions, if we are for the x far away from the centers, then from the known points, then these terms become very large. On the right hand side, we see a plot of functions which are taken. These functions are generated by drawing the some weights W from the posterior distribution. So let's say the most likely functions of which should be linear regression of our sine function, given the evidence of this one data point, are shown here. So we can see that these functions are pretty much random and not really following the sine function, because we have just one data point to consider, which is admittedly too little. Now, if we add some data points, we can see that here in our predictive distribution, our variance is getting smaller, and also the mean function is also changing. So we have 2 data points, and based on these 2 data points, these 9 Gaussian basis functions are forming us the likelihood function, are forming us this mean, and then in the posterior, which is then scaled by the basis functions, and then we also see how the variance is changing here between the 2 points is relatively small, and more far away from the points, this variance is still increasing. For the 4 input points as data, we can see that the function, the mean of our predictive distribution, is starting to somehow get the shape of our function. Also, the variance is becoming somehow small around the points, although it is becoming bigger between more far away between 2 points. And also what we can see when we are drawing the samples from the posterior of the weights W, that a lot of these functions are starting to look like our input sine function. Now, instead of 4, we will suddenly jump and have 25 sample points of this sine wave, and we will see how it changes our predictive distribution. So let's have a look at these 25 points. after having 25 points, our predictive distribution looks much closer to the actual regression function, the sign function. We see that the mean values of our predictive distribution are even sometimes closely matching our regression sign function, and our variance is overall rather small, and is basically just the variance associated with the term 1 minus beta. So here the this term is becoming smaller and smaller, and in infinity this term will become zero. So there will be zero variance, and this will be just a residual variance associated with the noise of the input signal. And if we are drawing now some functions from this posterior, as we did before, we can see that all of these functions are having essentially this shape of the sine wave. So with 25 sample points, we can very nicely estimate our function and characterize the uncertainty also associated with the prediction by having the variance for each value of x. The Bayesian approach to regression has an interesting interpretation in the form of equivalent kernels. So let's recapitulate that we have a prior distribution for our weights, which is having a normal distribution around zero with some variance, isotropic variance scaled by reciprocal of alpha on the diagonals of the identity matrix. And this is in fact having leading to a posterior mean, which is the Mn, and we know that the posterior mean is formed by the beta, which is the noise precision, and then of the measurements, and then we have the posterior variance and the design matrix times the t. So this has been already devised before for the case of the zero mean Gaussian model for the prior. The precision in such a case is for the posterior is governed by this function, where we have the variance of the prior and then the symmetric matrix from the design matrix multiplication with itself scaled by the precision beta. Now for the linear regression, or for the linear models for regression, we have the expression that the function, estimation function y is given by some weights and the input vector x, and for a new point defined as a vector of its coordinates, and then we see that this is a linear combination of these weights and the certain basis functions. Now, and we can formulate this as a dot product between the weights vector and the basis functions vector. Now, if we are looking at the mean weights, the Mn, then this term can be expressed as this term here. So this is the maximum a posteriori estimation of the weights, and this is in fact the mean of our posterior distribution, and it is equal to this term times the feature vector, and that can be also reformulated as that this design matrix is also represented as the feature vector of our training data. So this is the point which is the new point. This is the point which is associated with the training data, and the Tn here is the associated target value, which is associated with this xn. So we can see here that our function y is in fact equal to the sum and times the Tn, and we can see this entire term except of the Tn as a kind of a kernel where we have input 2 points, some training set point, or this all training set points, in fact, as this is the sum, and our new input point. And this kernel should estimate our new value y, which would be the value for a new input vector x. So in fact, this kernel is kind of a learned kernel from the training data, which we now here called as a x prime, where the x prime are all the points which are somewhat closer or far away from our point x. And this term is basically defining us this kernel function. So let's have a look how such a kernel looks like on the next slide. So we can see that the kernel function is now somehow a function of a distance between our input vector x and some of the or all of the training data input vectors. And then it is associated with some kind of a weight. And here we are plotting for our previous case with our Gaussian localized basis functions, how does this learned kernel look like from the posterior probability distribution. And we can see that for an xi of a value which is, let's say, close to 1, like here, this is 1, this is 0 for x. So for this value, xi equals, so let's say 0.8, this is the corresponding kernel, and we can see that if the value of x prime is becoming also close to this value of 0.8, the weight with which this Tn is its associated target is scaled will be high, and more far away it will be less and less considered. And we can see that some weights will be actually even negative and some weights will be positive, but the highest weight is associated when the x prime is actually equal to the xi. For a different x, we can see that this kernel is changing. So here we have the x is equal to the value of 0.5, and this is the corresponding kernel. So when the x prime will be 0.5, then its a value weight which its corresponding Tn is weighted will be the highest. And for all other ones, the weights will be much smaller, and sometimes there will be negative, meaning that we are even subtracting some values from this in the sum term. And this is the last case where we can see how this all works. So we have obtained this kernel now plotted here as a dependence on as a function of x prime from the Gaussian basis functions. But if we will take the polynomial basis functions or the sigmoidal basis functions, we can see that this kernel essentially looks very similar. It has a mean in the 0 where it reaches the highest value, and it has some kind of oscillations going on where the values are swing between positive and negative, small positive and small negative values. We can also study other properties of the equivalent kernel, such as, for example, the predictive covariance of outputs for any x and x prime. So we can see that the covariance between the outputs here is defined as the covariance of the terms like the linear combination of the feature vector for x and linear combination for feature vector for x prime with the weights w, and that is in fact we can see here that we can change this dot product formulation here so that we have first the weight here, and here we have the feature vector, and that in fact is equal to the expectation of this term, where this is the multiplication of the two terms. However, expectation of this term, this is just a can be taken out from the expectation. This term can be also taken out from the expectation, and the expectation of the W outer product is in fact our variance, posterior variance, which is multiplied from both sides by the feature vector, once from the feature vector of our point x, and then or from right with the feature vector of the data point. So this is the covariance, and it is in fact, we can see, equal to the kernel times the inverse of the beta of the parameter for the noise. So it means that this covariance is characterized by this kernel, and also we can therefore see that if we are taking some samples from the posterior over W and plotting the corresponding functions, then it shows us this covariance, the joint uncertainty in the posterior between the y values in 2 or more x values, and it is governed by the equivalent kernel. So this equivalent kernel is basically characterizing how these two outputs are correlated. Then we can also see that this equivalent kernel suggests an alternative approach to perform the regression. Instead of introducing the weighted basis functions, we can define a localized kernel directly for predicting the output values for the new input vector x. Some further comments about the equivalent kernel is that the weights of the kernel, which we have devised now from this from this regression, Bayesian regression from the posterior, in fact, the kernel for when we take all the training data input points xn, and we sum up the kernels associated with any x, these kernels will be summed up to 1. And we can see that how this happens if we, for example, take for all the tn equals 1, so we will have a constant function at the input. And as we have a bias term, which is the phi 0 equals 1, so this feature function is just equal to constant 1, then this function will be possible to be represented perfectly. And the predictive mean, therefore, for this function will be 1. And this predictive mean is, however, equal to this kernel with the corresponding values from the posterior times the Tn. And as the Tn is 1, then the outcome is that the sum of these kernels for any x is equal to 1. And then also please note that the equivalent kernel can be written as the multiplication of two feature vectors of an input vector, where this psi is equal to not the same as the phi here, but is very similar because it's simply just the square root of this function of this beta, which is the variance, and the covariance matrix Sn. The Bayesian approach allows us to compare different models, and this can be possible without actually reserving any validation set from the entire training set for comparing the quality of the models, but this can be done by considering all the data for the training. So imagine that we have a set of models, Mi, and from 1 to L, and each model Mi is expressing the probability distribution defined over target T with known X, so, or over joint probability Tx. So, and then we have the prior of a model, which we can define as a uniform preference of a model. So we do not have a particular preference which model to take in defining this prior distribution. Now we want to estimate the posterior distribution of this probability of which model will be favored. So the posterior distribution is modeled by is proportional to the prior distribution and the distribution which is called a model evidence, which is this probability of data given a particular model Mi. Once we have this posterior distribution, we can use it for in modeling the predictive distribution as an average or a mixture model of mixture distribution for predicting the T. So imagine for a given model, we have a predictive distribution, and then we make a sum of all models and weight them with their posterior. So we have a predictive distribution for one model weighted by the probability of that model, and sum together give us an average or mixture distribution. That will mean that if we, for example, have a two unimodal models as a predictive distribution, their outcome of this mixture model will be a bimodal distribution. So it is obtained as averaging predictive distributions of individual models weighted by posterior probabilities. Now, we instead of making a mixture distribution, we can also just select one model which is considered to be the best pick, most likely model. And this could be done by the so-called Bayesian factor, where we are observing these terms of this what we call the model evidence, or also marginal likelihood. So with respect to each model, and the bias factor, which is higher for the ratio, will give the preference to a particular model. So if this fraction is bigger than the 1, then the MI model is considered to be a better pick, and if it's smaller than 1, then the MJ is considered to be the better pick among these two. Now, let's have a look what this model evidence exactly is. So the concept of the model evidence is that it expresses how well a model MI, including its prior assumptions, explains the entire dataset D without committing to any single choice of parameters W. So we can see it here that we are having here the likelihood function of a given a data that they are generated by the particular weights and a particular model, and times the prior. And then we are integrating over all the possible weights, and that gives us the model evidence. Now, this model evidence can be also seen as when we look at the posterior distribution evaluation of the weights given data and a particular model, then we can see that it's equal to likelihood and prior in the numerator, and actually the integral of the all likelihoods and priors values for W, so drawing from the W set and associated probabilities, weighting it with the likelihood, that is in the denominator, and this is in fact equal to the model evidence. So it is interesting that this normalizing term is giving us some quality evaluation of a particular model MI. Another look at this model evidence. Now we are only representing it as a probability of the data as we had it before, without having the term MI here for the rest, but it is associated with one particular model. So, and we just consider one parameter of a model, a W, like for example, we would have a mu in the Bernoulli distribution. So imagine that during the Bayesian approach, we have our prior distribution, and let's say that this prior distribution is flat and uniform on a certain interval. Now, and this interval is termed as a delta prior. So this is the width of this interval, and then we have, so it's variance of this prior probability distribution is larger, and the posterior distribution is after we observe certain data, we are getting a posterior probability distribution, which is proportional to the likelihood times the times the prior, and it will, let's say, it will be sharp peaked and at some around the weights of maximum a posteriori estimation, and there will be some width around this high probability. So the weights around this W map will be considered also very likely. So we will have this peak of the probability distribution for the posterior, and it will be defined by the height, which is the W map, and it will be defined by the width, which is the delta W posterior. And this is just a very rough approximation of what is going on, but it uncovers certain properties of our model evidence. Now, if we have the model evidence here, it is equal to the integral of the likelihood and the prior with respect to the W. And this prior is, we said, is constant, and it's equal to 1 divided by the width of the interval of the prior. And so we take it out of the integral, and then we have just integral of this term here, which is approximated by a kind of a rectangle, where we have one side of this rectangle is the probability associated with the maximal a posteriori estimation for W, and then we multiply it with the width of this peak, and so the overall function of our model evidence will be the probability of t given the mean of the posterior, and times the width of this probability distribution, and divided by the width of the prior distribution. If we perform a logarithm of this term, we can see that this term will be a some. Here we will have some positive value, and this term, in fact, will lead to a negative value, because this will be definitely smaller than 1, as the width of the posterior is smaller than the width of the prior. So the logarithm of this term will be therefore negative, and it will serve as the penalizing term, if the peak around the posterior is very sharp, so the weights are really very much fine-tuned to one particular set of weights, then this means that that we are observing certain level of overfitting, and therefore this model, this part of the term will be penalizing the kind of a suitability of the model. And the more this width is narrower and narrower of the width of this peak, the more this posterior weights are fitted to the data, and the more this term is penalizing. So, and if we have not only one parameter W, but we have several parameters W, we have a vector of parameters, but their ratio between the the width of each of the component of W is somehow this ratio is always the same, then we can see that this penalizing term is multiplied by the number of the parameters, and it will scale m times more the more this posterior distribution is narrower than the prior. With the increasing model complexity, the first term, this term will be decreasing, and the second term will be in fact increasing, which means that it will be more and more negative in that sense. The model evidence is therefore the trade-off between these two values. If we have a too simple model, then this will be a higher value, and this will be a smaller value overall. If we have a complex model, then this value will be small, but this value will be large. So let's have a look at this in case of an example, a generic example. Imagine that we have a set of all possible data sets with associated probability that the data set was generated by a particular model. So we have a model which is generating the data sets. We can see it here on this plot. So we have all kinds of data sets, and we have the probability associated with that a certain model has been used for generating it. So imagine if we have the model M1, maybe we have only the in the case of polynomial regression, we have only the linear term and the constant term available, and this simple model is able to generate many lines, but only lines. And if we will have, for example, some curved function, or the data will be exhibiting some nonlinear behavior, then this will not be possible to be modeled by the M1. With M2 model, we can have some kind of intermediate complexity, let's say a cubic function, so we will have also polynomials of degree 2 and 3, and this is another model, and with that we can generate more models, and the probability of some model generating a data set is therefore also scaled. If we have a complex model like M3, which is a polynomial of up to degree 9, we can see that it can generate a lot of various data sets. However, as this is normalized, the probability of each data set is relatively small. So we can see here that a probability that some data set has been generated by the model M1 is very small, that is 0, because it's more complex than the M1 model can generate. The probability of M2 is the largest, and the probability of M3, the most complex model, is smaller. And then we can also see how this Bayesian factor, which is the ratio between the two model evidences between two models, is now showing which model is more suitable. So even if we have just for one particular fixed data set, the Bayesian factor is bigger than for some model MB than for MA, while the MA has been the model which was generating the data. On average, we obtain the the expectation. So we know which was the true model. So this was this one. So the probability of a data set generated by the given the model. So we can see that the BF expectation of a BF is here in as this term in the logarithm as a definition of an expectation, and but we have the probability distribution is is over the MA, as this is the true distribution. This is also actually a definition of the Kullback-Leibler distance, and we can see that here the if this value will be a positive distance, and the higher the value is, then this means that the MA fits the underlying model much better than the MB. If it is 0, that means that the underlying in case of 0, this means that the dataset can be equally well explained by the MA as well as MB. So they are practically, these models are identical. So we can see that this model comparison by this Bayesian factor can be effectively defining us which model would be suitable for a particular data. In a fully Bayesian treatment, we would calculate the probability distribution for t given some new x based on the prior input and target values and some hyperparameters alpha and beta. And as we will be estimating some probability distribution for the weights W in our linear model for regression, we will be, in fact, in a fully Bayesian treatment, evaluating an triple integral over the weights vector W and the hyperparameters alpha and beta, whereas the beta is the precision of noise and coming from the data itself, and the alpha is the precision of our weights corresponding to the reciprocal of weights variance. Now, this evaluation is very complex and analytically not tractable, and therefore we will be here talking about the so-called evidence approximation, where we use this marginal likelihood or evidence for estimating good values for the alpha and beta directly from the training set, and then we are using those in simplifying our Bayesian approach for linear basis function model by just having here the single integration over W, where we have our posterior probability distribution for the weights W, and then our conditional probability, which is governing our estimation of the value t given some new input vector x. So here the beta hat and alpha hat are these new estimates for these hyperparameters of precision, which have been estimated directly from the training data, and we didn't need any separate data for a cross-validation or on any other ways which would be limiting our data set, and we have it directly from the training data in a way that we will be maximizing the evidence. So now, if we look in the fully Bayesian treatment formula, we see here this posterior probability distribution for our hyperparameters. Now, this is proportional to the marginal likelihood or evidence function and some prior. This prior, in case this prior probability distribution is flat, we can therefore estimate our alpha and beta by maximizing the marginal likelihood, maximizing the evidence. So, and that can be performed. Here is the maximization of the evidence, where so here is the marginal likelihood, where we have our likelihood function for which is collecting the sum of square differences of our data and our estimated function, which will be then phi w, the linear combination of the features phi, and then it will be the standard deviation will be governed by the reciprocal of beta or reciprocal of square root of beta. And then we have our probability distribution of our weights given a certain hyperparameter alpha, which governs their precision or variance or standard distribution. And this formula can be reformulated, because we know that these are both normal distributions, can be reformulated into the following formula, where we see that we can take out from the integral already some constants, some normalization constants, beta divided by 2 pi powered by n half, and alpha divided by 2 pi times powered by m half. What is left in the integral with respect to the weights w is the error function, which we already know quite well, and this error function is also multiplied, each of its component, with the corresponding beta and alpha, as we are used to from the exponent of our normal distribution. So here is the data term of the error, the sum of square differences here, and here is the term which is coming from the error of the weights, and to keep them with the mean 0 and the standard deviation reciprocally proportional to the alpha. Now, we are now given a task to solve this integral of this error function, and by solving that integral, we will be able to perform the maximum likelihood estimation of our evidence function, such that we will be finding out what are the most likely alpha and beta hyperparameters. So, starting with that, we can see that our maximum likelihood estimation, our marginal likelihood is starting with the fact that our error function is minimized by using the mean, the mn, in the data term. We do not really know yet what are the alpha and beta, but we do know that the mn would need to be minimal. that's the mean of this posterior distribution, and that will give us the minimum error data error term. So if it's minimal, we know that the error function and its derivative with respect to w, if the w is equal to mn, it will be equal to 0 because it will be minimum. If that is true, then the following formula also minimal. And what we see here is the partial derivative of our error terms. So here we can first see our first error term, the data error term, and we see with respect to w this partial derivative, where we already have put in the mn, but it's a partial derivative with respect to the w, is equal to the it's deriving this. This was a square, so it will be 2 and then minus 5. So this minus 5 and transpose is here, and the minus is here, and the 2 is then cancelled out with the 1/2. Then we have the second term in our error term, and that is the term associated with the error of our, or distribution of our weights w around 0, and that w here is w transpose w, and after the derivative we have just the term alpha times mn. So we have also lost here one of these w's, and also we have lost this 2, which was cancelled out with the 1/2. So this should be equal to 0, and this could be reformulated to a formula where we put together all these terms and take out the mn, which is minimizing this, so it's equal to 0, and then we can recognize here that this is in fact our function or formula or inverse of that of our posterior variance, Sn. Sn was inverse of this term, you might remember. And this is no longer equal to 0, but this is equal to beta times matrix phi transpose T. And in fact, this is simply the formula, which is, we recognize here the linear regression terms here as well. So with that, we can state that this is equal to some matrix AMN, and we know that the A will be then inverse of the posterior variance, so it's in fact the posterior precision matrix. Now, to all this, we already understand what is the mn then equal to here from this formula, and now we have for our data term here, we can look what is the data term equal to if we replace the w this square in the square with mn plus some delta, because we know that the w is centered around its mean, So any W can be expressed as its mean plus some offset from the mean in form of a vector. So if we put this replacement into this formula, we realize that we can reorganize this and design matrix the phi and sigma. So we multiplied this design matrix with both of these terms first. And now we can multiply this out and further find out how we can reorganize this square term. Before we do that, however, we also realize what is the square term with respect to the weights equal to, and this is simply equal to the mn and mn plus delta. And that can be reformulated into the square term for mn, and then 2 mn delta, and then square term for the delta, the offset from the mean. And therefore, we can reformulate our error term EW into mn plus delta into the term where we have the beta half t minus theta matrix times mn minus theta sigma, and then the whole term squared. This is our data term, and here we have our weights term squared as well, as we devised it just before. And then we can also reformulate this term further on into other terms, such that we isolate out the mn from the delta. So if we now perform this, then we will have one term t minus theta mn squared. So imagine that we are now multiplying out the terms here in this squared term. So one term will be certainly t minus theta m squared. This is like an x minus y squared would be x squared minus 2xy plus y squared. So this is the x squared is here. And now we do the same for our weights term. So we have here mn square term. And then we collect the linear terms here, where we can see that the beta is multiplied with t minus beta is multiplied with t minus capital theta matrix mn. So this is this term times this term, but then 2. So this is the cross term, but the 2 is cancelled out with the 1/2. And so this is one cross term. And then we have another cross term here associated with alpha. And then we have the terms which are associated solely with the delta, the offset, and no longer with the mn. Now we can realize that actually this is exactly the formula for our error term, except that it's not the error term for the W, but for its mean, mn. So we can reformulate this part as being error term of mn, and then we have this middle part here, and then this we can reformulate as well. So this last term, two terms in fact, we can reformulate into, put them together, because we can see that there is this square term for the delta. So we put the square term here from both sides, and inside we will have our beta and alpha, and then the positive definite matrix calculated from the design matrix transpose times this design matrix, and here we will simply have identity. And in front of the whole term, we have 1/2. So this is one part, this is another part, and this is the cross term associated with the linear term of the delta vector. So we can now move this part to closer to this EMN, and in fact this part here we can recognize, well, what is this delta? Delta, as we defined here, is W minus Mn. So this is W minus Mn transpose, is this delta transpose, and then we have some matrix here, and in fact this is the same matrix as we see here, and therefore this part is we call this matrix A. And then we have the W minus Mn. So, and then we have this term here, which is minus T minus the design matrix times Mn transpose phi plus alpha Mn transpose. And this term, we already know, in fact, that this is exactly the same term as this after certain small reformulation here. So if we put this part on the other side, for example, and we have instead of this transpose here, we have the non-transposed vector. We can do these operations simply by performing the transpose of this whole thing. Then we will realize that this is equal to 0, and this is therefore equal to 0 transpose, which is still 0. So this cross term will be equal to 0, and we will be left out with the convenient result that this this error W is equal to error term Mn, which is has these two data term and the weight term, and plus the 1/2 W minus Mn T times A W minus Mn. So this looks exactly like some exponent for a normal multivariate distribution. And we will see that it indeed also is one. So here we performed a long clarification. What in the book will be then simplified to a simple statement that the EW is equal to this term, and it will be unclear why is that the case. So now we know exactly why is that the case. Following from the previous slide, we had in the beginning the formulation that beta design matrix transpose times T is equal to the A times Mn, where the A was represented in a more complicated form, but this complicated form has uncovered that it's in fact this posterior variance inverse, which is the posterior precision matrix. And then, therefore, we can reformulate this term such that Mn is for us here the beta times A times design matrix transpose T. Now, let's have a look at what we actually want to calculate here. Our goal is to calculate our marginal likelihood, because out of this marginal likelihood, we can perform logarithm, and then we can perform derivatives so that we can maximize this marginal likelihood such that we will find by that the corresponding arguments, which are alpha and beta, for which the marginal likelihood will be the largest one. So, and we need to devise formula for those. Before getting there, we already see that have seen that this marginal likelihood is this has these constants in the beginning, and then it had some integral which we need to solve. This is the integral which we needed to solve. And now we have decomposed the EW into EMN plus the rest of this EW, which is 1/2 of or minus 1/2 of the such a square term where we had this delta on the previous slide. So now it's W minus Mn transpose A, and then W minus Mn. So, and we could have taken out from the integral this exponent part, because this doesn't have any value W anymore, and we only keep in the integral the terms which are associated with W. And luckily, we can see that this form is a very nice completed square form, which gives us the immediate chance to devise what will be the terms which will be like the normalizing terms of this this integral, and corresponding to this integral, such that such a probability distribution would be equal to 1. This normal distribution would be equal to 1. And these normalizing terms inverse are actually the value of this integral, the reciprocal of these normalizing terms. And therefore, we can find out that it is equal to, actually, the integral is equal to 2 pi powered by m½ times the determinant of A powered by minus 1/2. Now we can put this into the solution of our marginal likelihood here, and now we no longer have any integral. And on top of that, we also see that this term can be also canceling out with this term. Now nothing stands in the way to perform the logarithm of the marginal likelihood, where we are putting in front of the ln A here the exponent m½ in front of the, and the A is only here because the 2 pi has canceled each other out here. And then we have the beta, which is ln beta times with the multiplier n½ coming from the exponent, and this 2 pi we will have as well in part where we have no negative terms. So here is the n½ ln 2 pi. And then we have this term, which is an exponent of an exponential function. So this will be just taken into the down from the exponent in this logarithm. And then we have minus 1/2 ln A. So we will need to calculate what is this minus 1/2 ln A in terms of derivative with respect to alpha and beta when we want to perform the maximum likelihood estimation. So let's get into that. Before that, however, we can observe the behavior of this logarithm of the marginal likelihood, which is this formula here. So, and we will see that on a sinusoidal example, which was the synthetic example from the chapter 1, where we have the sine waves, and then we have one sine wave, one period, and we want to approximate it by some mth degree polynomials. And we can see, so the m is the complexity of our model, and we can see that how is this evidence characterizing us somehow the quality of our model. So we can see it here very nicely in this logarithm of the evidence, where we start with here is the function of m, so m is increasing from 0 to 9, and here we have the corresponding value. As it is a logarithm, it will have a negative values here, but still the highest negative, I mean the least negative value will be the smallest negative value will be performing, showing us what is the best parameter for our model. So this evidence can give us that information. So we start with the m equals 0, and I need to say that here the prior alpha was fixed to 0.05, so the weights are kept relatively small through this prior. But we can see that the m equals 0 is simply a bad fit. So it's a constant function which is approximating this. And we will see that this value also corresponds to quite a low value for m equals 0. Now, for m equals 1, we see that this marginal likelihood, the logarithm of it, will increase in its value, despite the fact that, and as you can see here, this term m now is not 0. So before this term was equal to 0 because m was 0. So this term in the penalty was actually not decreasing the value, but the lack of fit, so this term here and these terms were simply dragging the value to be a very bad fit. Now with m equals 1, we are so m is no longer 0, so this term is also part of the penalty. It's also a negative value because we can see that alpha is 0.05, so this is a negative value. However, despite that, the fit with a linear with a line is so much better than it increases the quality of the model, despite the fact that the complexity of the model has increased. And now we have a quadratic term added, and we see that the complexity of the model has been penalizing the quadratic term because the fit was not improved very much. And then for cubic, we can see that it has improved the fit so well, but it still has relatively small m, so that it is having overall the best score, if you like. And then the other functions are still also good, but the other models with higher m's are still good, but this added complexity term will be gradually making them less and less suitable. So we can see how this marginal likelihood, plotting it, in fact, it's a logarithm, in fact, can nicely show us what is the best parameter for a model like a polynomial degree. Now we will apply the maximal likelihood estimation approach on this evidence function, on the marginal likelihood, such that we want to find the corresponding A, so alpha, which will be the maximizing our evidence function. So let's recapitulate what is A. Here, it's in fact the alpha times the identity and plus beta times the positive definite matrix as a result of the square of the matrix, design matrix phi. As this is a positive definite square matrix, that means that it can be decomposed by means of eigen decomposition into two orthogonal matrices and one a matrix which is a diagonal matrix, which will contain the eigenvalue entries. That also means that we can reformulate our matrix A to be equal to the an orthogonal matrix on one side, and then we have the diagonal part, diagonal matrix, and then we have the again the orthogonal matrix. Out of this, we can state that the diagonal entries of our posterior precision, so because this is our posterior precision, as we know, diagonal entries of our posterior precision are, in fact, on each entry is simply alpha plus beta, and then the entry on the diagonal. So for the first row will be lambda 1, for the second row on the diagonal will be lambda 2, etc. But they will all be multiplied by beta and then added alpha. So we can see it clearly from this formulation here. And therefore, we can, because for our, if we want to perform the derivative for maximum likelihood estimation, we need to find out what is the ln determinant of A with respect to the alpha. And that is equal to, here we can see, it's ln of a product of alpha plus beta lambda I. Why is it a product? Because the determinant of a matrix, of a diagonal matrix, which is surrounded here also by the orthogonal matrices, but they have determinant of 1, both of them. So this is actually the determinant of our matrix A, and that we know that it is a diagonal matrix, and determinant of a diagonal matrix is a multiplication of all diagonal entries together. Therefore, here we have the product of all these entries together, and that we can also we now know how to integrate that, because it is simply the will turn into a sum. So once we take this out of the logarithm, we will have a sum instead of the product of these individual ln's of these arguments, and that will therefore be derivative of several summed up terms, and all these summed up terms will have the formula 1 divided by alpha plus beta times lambda I. So now we know what is the ln determinant A equal to when we derive it with respect to alpha. Now we can put it back into this equation, because this equation we need to perform derivative of in order to find out what is the minimum or maximum and extreme in this case, and what then we will find the corresponding alpha. So if we are integrating this, then this term will become m divided by 2 alpha, and then we have this term will go away, and then this term, in fact, we say, because it contains alpha, mn contains alpha, but the book is also describing that we neglect the derivatives of this square term with respect to alpha, as the resulting formula will be anyways correct at the stationary point, at the mm. So, and therefore, we only have this integral of this minus 1/2 ln A, which is this term. And this is equal to 0. So now we will find out what will be, therefore, the alpha equal to, in this case, of the maximizing marginal likelihood or evidence function. So, and that comes to an outcome that we have the alpha times mn transpose mn is equal to the m minus a and the sum of the of our ln terms which we had before, the diagonal entries, or the reciprocal of those. And how did we come to this outcome? So first of all these entries were previously together and they were equal to 0. So this one was on the other side. And the alpha, this alpha was like m divided by 2 alpha. And now we multiplied by the 1/2 or by 2 the entire formula, and then we multiplied by alpha. Therefore, we had the term minus alpha times mn squared, and then we had this term also was gaining 1 multiplier alpha, which we could actually put here. And we will do that because we can see here that now the m here, what is it equal to? If we would see that this is a sum of from I1 to m, then we can put it inside as 1 plus, because the m will sum up to the to m. 1 plus 1 plus 1 plus 1 m times will become m. So we put this multiplier into here and we extend this sum such that we can fit the m as well as 1 minus alpha divided by alpha plus beta lambda I. And if we do that, we can also put the 1 onto the into the fraction, and 1 will become alpha plus beta times lambda. And as there is already 1 minus alpha, we will end up with having this to be equal to sum of beta lambda I divided by alpha plus beta lambda I, and this sum we will for now call gamma. So therefore, out of this we will find out that alpha is equal to the gamma divided by the square term of the mn, the mean posterior. However, the mean posterior itself contains alpha, as we said already before, and in fact gamma it contains also itself alpha, and therefore we will find alpha not just by a formula which is which gives us this term explicitly, but we will find it iteratively by just giving some value of alpha, and then we will find out what will be the corresponding gamma and what will be the corresponding means given that alpha, and then we will again calculate out of that alpha until we find a stable solution for alpha. So we have to find it out iteratively. And we can do it. One simplification is there that our design matrix will not change, and therefore the matrix, which is the product of the design matrix squared, will also not change, because and out of that matrix we are calculating the lambdas. That means that those will not be changed, so we can pre-compute that. So and the nice thing is about the alpha that we have found an alpha, the parameter, what would be the best parameter for maximizing the evidence. And why do we want to maximize the evidence? We have seen that maximizing the evidence, or the log of the evidence for that matter, leads to the best model. So we want to have the best model, which will be the m equals 3 in the case of polynomial functions, and but that we can either read off from that plot and then not involve any other computations, but we don't know the alpha. We have their defined alpha to be certain value. So in order to find out alpha, we can find it out here just by analyzing the training data. And from the training data, we have found out what is the maximal marginal likelihood or the maximal evidence, and then by maximal evidence corresponding to it will be this alpha, which we find by several iterations over this term. Similarly, we will find also beta. We find beta in a very similar way. So we again perform the derivative, but we first want to know what is the ln derivative of A matrix with respect to beta. And that is equal to the ln of the product of these diagonal entries, which we already understand why. And that is equal to because here we have the so we put this product into in front of ln, so it will become sum, and then we have the sum of ln terms here, and that sum of ln terms, so each term will be then derived independently and then put into the sum, but here we will find out that ln this is equal to lambda I divided by, so 1 divided by this term times lambda I. So this will be the term. Here is a little difference because previously we have seen here that it was 1 here, and now we see here that there is lambda I. But then now we know what is this term equal to for when we derive with respect to beta. So now let's derive this ln marginal likelihood, and we will perform that, and we will have here the first term will be coming from this term, and then we will have the second term, which is the error, but now the error term where we have the beta is associated is the square, is not is the data square and not the square of the mn's. And then we have this this term here where we found it naturally because we already know it, that it's this one. Now again, the mn also contains beta, and therefore as it contains the variance matrix, posterior variance matrix in itself, and but we will neglect that too. Now at this point we will again multiply it by 2 beta, which 2 will cancel out all of these 1/2 because this is supposed to be equal to 0, and then we multiply by beta, so we have just n, and then beta times this term, and then beta times this term, and that will be equal to actually gamma, which we already introduced before. And now we have the gamma, and therefore we simply will find out that beta is equal to n minus gamma divided by our data square term. And again, this because the gamma contains the beta and mn contains the beta too, and therefore we will need to find out beta by several iterations. So we first initialize it with some beta, calculate out of that the gamma, and out of that we calculate the mn, and we calculate our square term, and then we update beta. In fact, we can do it in such a way that we are simultaneously updating alpha and beta together until we find a stable solution for both of these. And that will then, those will be the parameters which will be maximizing our marginal likelihood, maximizing the evidence. And as we see, maximizing the evidence is a good thing because it will lead to the best performing model overall. So now let's have a look how we combine this together. And we can see that if we have our positive definite matrix, which is the square of the design matrix, then it has positive lambdas. And this positive definite matrix is in fact governing the shape of our normal distribution for the W defined by the maximum likelihood estimation. Now, here we can somehow see that the lambdas, which are small, will also result in low curvature, will result into elongated axis. So the lambda 1 is small and lambda 2 is big. As lambda 1 is small, this will imply that it's not really very much determining our model. The data are not really very much characterized by this dimension, and therefore for the version for the dimension U1 here, or for the W1 here, we will have, it will be the maximum a posteriori estimation of W will be dragged towards the prior, where the prior has the mean of 0. So this is the mean of the maximum likelihood estimation, and then this is the mean of our prior, and or of our likelihood function. This is the mean of our prior. We can see that with respect to this dimension, it's dragged towards the prior. With respect to the other dimension, for lambda 2, we see that the lambda is high, and it has a high curvature along this dimension, and therefore the axis is also small. And that means that the lambda is or that dimension itself is influencing the data itself is very much determined by this dimension, and therefore the maximum a posteriori estimation of W will be dragged a lot towards the maximum likelihood estimation away from the prior. So, and why is that the case? So let's have a look at our matrix, which is the gamma matrix. The gamma matrix, sorry, the not matrix but fraction, which is, and gamma is sum of these fractions here. So if we have the very high lambda, then this term will be 1. And if we have very low lambda, then this term will be going towards 0. The higher the lambda, the higher the gamma. Because if gamma, as this term varies between 0 and 1, and gamma is simply sum of m of these terms, then gamma varies between 0 and m. And if the alpha is much smaller than the product of beta and lambda, then the corresponding W weight for with respect to that lambda, with respect to that let's say polynomial degree, will be dragged towards the maximum likelihood weight, will become the maximum likelihood weight if it's much smaller, and if alpha is much bigger than this term, then it will be dragged towards the prior. And that is quite intuitive, because we know that if the prior is strong, then the weights will be small, and then if the prior precision is small, then it will be dragged more towards the data maximum likelihood estimation from the likelihood function. And in fact, the effective total number of well-determined parameters can be obtained from the gamma function. So imagine that we have 9 polynomial degree, which we want to use for our sine wave, but we will find out by this that there are the gamma is not equal to 9, but it's equal to a much smaller value. That means that is the effective total of well-determined parameters, and we should use those parameters and not more parameters for a given regression problem. So, and that means that the effective total number of well-determined parameters gamma define that the m minus gamma parameters would be set to quite small value by the prior. So in that case, we will have some of these weights will be small and some of them will be big. And if we have the situation that we have a lot of data points, much more than we have the possible complexity of our model, let's say 9th polynomial degree is the largest, but we have millions of data points, this leads that this will cause that we will have a very large design matrix that will lead to a positive definite matrix, which is the square of the design matrix, which will be having very high values of the lambda on the diagonal after eigen decomposition, and that will lead to the fact that the gamma will become having the value m. So and therefore, in such a case, we can approximate that the beta is equal to this term, where we have removed the minus gamma because it's too small with respect to n. And here we have the alpha is equal to this term, where we have replaced the gamma with m. And then we only need to update the alpha and beta with respect to the posterior means here. Let's have an insight about this behavior of our evidence approximation and our definition of our hyperparameters here, like what is happening with the evidence. So we can see that we have set now one of these two hyperparameters to some fixed value, which has been obtained by this maximum likelihood estimation process. Again, we have our sinusoidal synthetic data, but now we have 9 Gaussian basis functions instead of the polynomial functions. But still, we have the complexity of basis functions is 9. So m is 9 or 10 because we have bias. And then given we have beta, we are looking at what happens if we are changing alpha or ln alpha. And we can see that for small values of ln alpha, our gamma function is quite high. Well, because we are not dividing by a strong denominator as the alpha is small. Now, if we are dividing by large and larger value in the denominator, naturally this function will be going slowly to smaller and smaller value. At the same time, if we have this term, which is the a times the m squared, the posterior mean squared, then with increasing alpha, we will see that this term will be also increasing. And they are meeting at some point, which is this point here. And we can see that in fact that's the same point for which we are maximizing our marginal likelihood function, which is generally a good signal that we have obtained the best model parameters. So this will correspond to the best alpha here, and that corresponds to this maximal value here. And we can see, just for comparison, that the test set error here is having the ideal value, the smallest loss is just very nearby the maximum. The last plot is showing us that if we are increasing gamma, then with that we will be increasing more and more the model will become more permissive to complexity. So if the gamma is larger, that means that we have a more complex model compared to the gamma which is smaller. And if gamma is small, very small, then all the weights will be equal to 0. And then if our gamma is larger, then we can see that the weights are becoming gradually will be increasing in their absolute value. So these are the different weights. Here is the weight 0, this is the weight 1, this is the weight 2, and so for all the 10 weights for these 9 quotient basis functions. And with this, we have completed the discussion about the evidence approximation, about the Bayesian treatment of linear regression, and generally about the linear models for regression. It remains to be said that while this seems to be very powerful, overall powerful framework, and we will continue with linear models for classification as well, we can also mention few possible disadvantages of the current approach, especially of our fixed basis functions. So fixed basis functions are limiting because we didn't define the data yet, and we already have or trained the data yet, and we already have some basis functions. So these might be not very suitable, and in the end, given certain data. And ideally, the basis functions are also designed by the training data. And also, we can see that we define certain model, and we have possibly a large amount of parameters, increasing possibly exponentially with increasing dimensions. And some of these parameters might not really be very much expressing the dependency of the weights on the data. The weights will be generally small, but still we will need to have that parameter values. So having fixed amount of basis functions is also a disadvantage. So because the target variables might have a significant dependence on only few basis functions. This concludes the chapter 3 on linear models for regression, and I see you on the next chapter on linear models for classification.